With that discussion of the superstring. So just since I give you a 20-minute reminder of the things we've talked about 2 months ago before, so that we remember everything that we discussed. Okay, so you remember that the superstring is based on the world sheet performance field theory. The world sheet actions of the superstring, the matter part of the world sheet action, involved fermionic fields as well as the transfer scalar fluctuations. The fermionic field, the matter part of this thing was simply 1 by 4 pi prime into sigma okay, and then there's 1 plus. Then we have 1 plus 1 by 2 pi psi del sigma del sigma plus psi bar. Okay, this was the matter part of the function. Okay, just get all the facts. So, I'll remind you of the OPs. This is the first one we're familiar with. And the fermions have psi mu. Psi mu z, psi mu 0. Okay, and the stress tensor of this theory is equal to the holomorphic stress tensor there was the fermionic part of the stress tensor, the thing whose 0 mole is the supersymmetric operator sector. And the expression for that is equal to. Okay, and we discussed how this theory was a superconformal field theory, which meant that there was the following OP, the bosonic part, had the usual OPs, so the difference is 3 by 2 dimension by 2 second to the fourth plus 2 to the z plus del 2 by z, and the stress tensor with the fermionic current TF had the OP of the stress tensor with primary of weight 3 arms. TF of z is equal to 3 by 2 TF z by z squared plus del TF by z plus blah. The new thing in the algebra was TF with TF, which had an interesting form. We have TF of z with TF 0, meaning so there was the anomaly term, which in our case was d by z cube, and then we get plus of this 2 by z t0. Okay, and we talked about how these commutation relations, while they're true and we showed them just established them just by hand for this simple free-field theory, had a generalization where you regard this quantity here as the central charge, or sometimes you introduce okay, so just if you everywhere you see 3 by 2d, you replace that by c, or d by 2 by 3c. That gives you an algebra that is implemented in many different theories, with this C being the central charge of the system. we introduced C hat, which was 2/3 C, which was a measure of how many post-Fermi pairs you have. Okay? And sometimes we rewrite formulas in terms of C hat. So a single boson fermion has C equals 3 halves with C hat equals 1. It's just definitions. Okay? And this was the matter content of our worldsheet, of the theory of the worldsheet of the superstring. Any questions or comments about the matter part? I'm going to review the course part in a moment. Any questions or comments? I'll also remind you of the state operator matter. But any questions or comments? Okay. Fine. So in addition to the matter part, there was the coast. There was the coast sector of the worldsheet theory. So we have the usual BC coast, and we have the supersymmetric where they're superpartners, the beta gamma. So remember that one way of thinking of B was that it was, B one corresponds to the moduli units, those parts of the metric that could not be reached by a diffeomorphism starting from your standard form of the metric. And so in particular, B secretly came from a field that was BZZ. And so that made 2. On the other hand, C came from those diffeomorphisms that were left unfixed by regions. C was then therefore a vector field. It secretly came from CZ. And so it went minus 1. Upper indices are weight -1, lower indices are weight 2. Okay? So the supersymmetrization of the structure, what to expect from it is sort of, supersymmetry transformations are labeled by not a vector field but a spinor field. So gamma should have weight half and beta should have weight 3 halves. As discussed. Now the DC system, you remember we talked, has a generalization to arbitrary lambda. Right, where P has weight lambda and C has weight 1 minus lambda. So we asked the more general question than the question that's relevant to string theory. We asked, given a BC system of arbitrary weight lambda, can we complete it into, and we guessed, into a system which was supersymmetric with partners of weight lambda minus half and go half 3 by 2 minus 1. Okay, and we discovered in some earlier class that we could. This field had been given the name beta. This field is gamma. Because beta will be lambda is 2, so beta will be of weight 3 by 2, and gamma will be of weight minus half, as we said before, for the theory relevant to string theory, but we can do it in general, so to speak. Okay? And we found the Lagrangian and the stress tests of the system that achieves this. The Lagrangian was really simple, the same as that for the DC system. It was beta del gamma. I hope it's order right. Del gamma plus holomorphic. We had the same Lagrangian for the DC system. B del bar C. By the way, in the BC system, it doesn't matter if we write B del bar C or C del bar B. But in the beta gamma system, it makes a difference. Can somebody tell me why? Firstly, why in the BC system? Good. So let me give you the completed.
So D and C are the ghosts of a fermionic state, so they are bosonic.
D and C are the ghosts of a bosonic state. So
D and C are the bosonic state, they are fermionic, and beta gamma are of a fermionic state.
Good. And because these are fermionic, when I integrate by parts, I pick up a minus sign, and then I interchange the two, I get the reverse minus sign. So B del bar C del bar B, the same thing. However, here, if I integrate by parts, I pick up a minus sign, and then I can reverse without any further minus signs. It's opposite. So beta is distinguished compared to gamma. B and C, there's no distinction. As far as OPs go, the stress tensor, we invent a distinction, give them different weights. But just as a Lagrangian and flat space, B and C are isomorphic, beta and gamma. Okay, as Loeb diagram reminded us, the BC fields are anti-commuting, whereas the beta gamma fields are commuting. And I'll just remind you of the stress tensor and the fermionic part of the stress tensor of the system. So the stress tensor is del BC plus lambda del of BC. That's just the BC part which we're quite familiar with. Plus del beta and gamma minus half into 2 lambda minus 1 of del of beta. And then there was a fermionic part, there was a fermionic current, which was minus half del beta C. So the fermionic current as usual mixes one fermion with one boson. So minus del beta C plus 2 lambda minus 1 by 2 del of beta C minus 2 B. And in some earlier class, we had checked that this system, we either checked or I left it as an assignment for you to check, I'm not remember which, that this system obeyed this algebra as well, but with a central charge given by Okay? Now, of course, this was all abstract for general lambda, but lambda is 2 in real life, in real superstring theory. So, lambda equals 2 given minus C equals minus 15. As usual, we require the worldsheet theory and the theory of the worldsheet superstring to be C equals 0 with normal field theory. So you could ask what dimension that works. That works in 10 dimensions because every dimension contributes 3 halves to the central charge. That gave us the critical dimension D equals 10. This superstring there. Okay? Good. So much for these systems. Was there anything else I wanted to say about writing that? Okay, that's it. Any other questions or comments about this? Any questions or comments about the BC system? Just for the ground theory, central charges, and so on. Okay. Then the next thing, I'm not sure it was in exactly the same order as presentation in class, but or in one logical order. The next question you might ask is, well, we know what our theories are now. Can we understand all the vertex operators? Okay. So basically, what we wanted to do was to understand the straight operator map in detail. Okay. So what about the straight operator map? Well, for the X system, some time a year ago, we understood this in thorough detail. The backing of the theory maps to the identity operator, blah, 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 blah. Okay, alpha minus 1 maps to del x, the state e to the power, the operator e to the power kx maps to the state with no oscillators, but zero momentum, the right set momentum with ID vector k. Okay. What about the fermions? So, one of the things that we, in our crude introduction to superstring theory, one of the things we'd already talked about was how we're going to have to deal with fermions that are both antiperiodic as well as periodic on the spatial settlement string. Let me remind you of the argument of that. You see, and in computing, let's say we were interested in computing a one loop partition function of the worldsheet string. We wouldn't be interested in this because that gives us the one loop partition function in space time. So this is something we need to do for physical calculation. Okay? Now you can ask, what spin structures? You know, what periodicities do you have to do this calculation? Okay. And the point was that since we were interested in computing a partition function, if we were interested in computing a partition function for the world sheet of the string, then that is a partition function in a theory with fermions automatically is a path integral with anti-periodic boundary conditions. So the natural thing to do was to compute something with anti-periodic boundary conditions at the time. And then you might have wondered what boundary conditions we should use around the space set. You make any choice you wanted to start. Let's say we choose this. But this object is not modular invariant because it chooses a particular cycle. It says this guy should be plus or this guy is minus. Clearly, we're just tilting the torus on its space. This mixes with minus plus. So, in any modular invariant partition function, as we've seen before, modular invariant is a key ingredient, key technical ingredient in string theory. We must also have to deal with minus x. Actually, it's less immediately obvious from this. Minus minus also mixes with these things under modular transformations. Actually, a way to say it is that suppose you've got minus minus, then what's the boundary condition around this thing? It's class fit. Yeah, because antiperiodic as you go around this cycle, antiperiodic as you go around. So it's class as you go around this cycle. The modular transformation that makes these the two fundamental cycles of the torus will have plus minus. So these constructors all mix with each other under modular transformations. So if you're doing a path integral and you want it to be modular invariant, you better have all these three constructors. In order to give this thing a partition function interpretation, we also needed to add the one constructor that's modular invariant by itself, maybe plus plus. And then the sum of these four can give you a modular invariant partition function. And we discussed in some detail how this plus this with a factor of half is a partition function with a projection keeping states of a given value of minus 1 to the power of f. Right? Because this quantity is the usual partition function in the period. No, sorry. Yeah. This quantity is the usual partition function. The other one is a partition function weighted with minus 1 to the power of f. Similarly here. Okay? So we've already motivated the statement that what we're going to need to do in string theory is to consider states both in the sector in which the fermions are antiperiodic, as well as the sector in which the fermions are periodic. Plus impose a projection on the states by projecting on the states of a definite value of minus 1 to the power. Okay? Remember, we motivated this. We're going to see this in full technical glory in some relatively soon point. No? But just I want to remind you the motivation so that you remember why we study the fermions into the two sectors. The sector in which is periodic in the circle, as well as the sector in which is antiperiodic in the circle. Okay? You remember the sector in which is periodic on the circle had a name, it was called the Ramon sector. The sector in which is antiperiodic on the circle is called the NS sector. Now, we want to work out the state operator mapping with these two sectors. And the NS sector were typics. Just remind you of that. The first question you ask is what is the state corresponding to the identity operator? Okay? So we've got fermions because we're in the NS sector, the half integrally molded, and psi z is equal to sum over psi r z to the power r and then plus r because the fermion field is big. That's an expansion of a psi field. And that tells us that psi r is equal to 1 by 2 pi integral dz psi of z z to the power r. From which we see immediately that the identity operator, we argue by that the identity operator was in the NS sector. And we see immediately that the identity operator has the property that psi r for r on identity equals 0 for r greater than infinity. half, and psi or one identity not equal to 0 or less than equal to minus half. Simply from the fact that psi by the equations of motion is an analytic inserted into any correlation function. So inside a correlation function will be identity inserted in the middle, which is equal to nothing inserted in the middle. Psi is completely analytic, so this is inside any correlator, this is an analytic function. So if r is greater than or equal to half, this is also analytic, so you just get 0. But if r is less than half, we get both. Okay? And that told us that this is of course a very familiar thing. If you define a vacuum state by the same condition, which is natural, because these are all creational. These are all annihilation operators, and these are all creation operators. Maybe these carry negative energy, these carry positive energy. Okay? Then this also gives you, this is also the state that's the lowest energy state. Okay? So this is an illustration of this usual fact that any unitary conformal field theory, the identity operator is, unless you do something funny to the theory, is due to the vacuum state. Okay? And then we determined all the other, right? So there was a state which was psi minus half of the vacuum, and that was due to the operator psi of 0, and so on. Psi minus 3 halves was dead psi. Products of products, blah, blah, blah. Right, so the inner sector was really simple. However, the Ramon sector was less simple. Because the Ramon sector, when we thought about it, required that all states in the Ramon sector were dual operators, which, when inserted at the origin, gave you a branch cut singularity as you went. Because that's the only way you get these operators to act in these states. Right? Because the moning in the Ramon sector is integral, but there is this extra factor of half. So those operators act only if there's a branch cut singularity with psi. And we didn't know how to understand these. I mean, actually it's quite a general fact of quantum field theory, a fact that is becoming more and more appreciated, applies to high dimension quantum field theories in intricate ways. Is that, statements about, if you define a path integral, you define a local operator is just an instruction of how to carry out a path integral. So if you define a path integral with a particular singularity that is very well specified, then that defines an operator. Okay? It's just because then an operator in the end is an instruction on how to carry out path integrals. So the instruction is carry out path integral over all fields that have a particular singularity structure. That's a well-defined operation, it defines an operator insertion. So a well-defined local operation defines an operator insertion. Okay. There are many situations in one field theory where the only known way of describing those operators is by such descriptions, telling you how the singularity ends. Okay? If you know how Toft loops are examples of such operators. It's quite singular. Okay. This, in principle, we don't need to say more. This prescription defines the operator. But that's a pain in the neck if you want to calculate. Every time you have to start thinking of doing a path integral some singularity structure, it's not so pleasant. It's enough, but it's not so pleasant. So always nice to have an explicit expression in terms of free fields. Okay, for the operator. And so for that reason, we decided to sit in Bose-Weiss. Okay? So what was the Bose-Weissization? We demonstrated, and I won't go through the details of that demonstration, but we demonstrated that if you had just an ordinary scalar field, I think we call it H, okay, such that H with H is equal to minus log of Z. H of Z with H. 0 is minus log of Z. It's like alpha prime equals 2 in this kind of fields. Then a system of two fermions, psi 1 and psi 2, we found it convenient to group them up into psi 1 plus I psi 2, psi and psi 1 minus I psi 2. cycle, the other way have been square root 2, which you've forgotten. Okay. Now, the theory of these two phenomena is identical to the theory of a single analytic scalar, H. The first test of that was the central charge is agreed. Single boson is central charge 1, two fermions is central charge 1. But of course, there were many theories of equal central charge. These two theories are equal. Under the map, psi 1 of z times psi of z equals e to the power I h z, psi tilde of z equals e to the power minus I h. Okay, a simple check of this map was that the dimensions agree. What's the dimension of e to the power I k h? Somebody? K squared by 2. And when you said alpha prime 2, it's k squared by alpha prime k squared by 4. You said alpha prime equals 2, it's k squared by 2. Okay? Just k squared by 2, but k is 1, so it's half dimension of psi, k is 1, it's half dimension of psi. Okay, other test that worked was looking at the OPs. Psi with psi is orders, OP is order z. Psi tilde with psi tilde is OP order z. Psi with psi tilde is OP of order 1 by z. And we checked that is true of these things. And in fact, just those statements plus some assumptions of good behavior at infinity were enough to demonstrate that all correlation functions of psi and psi tilde are identical to correlation functions of e to the power I h and e to the power minus I h in these two different theories. We also asserted that every operator in each of these theories could be built out, could be obtained from OPs of sufficient numbers of psi's and psi tildes, or sufficient numbers of I e to the power h's and e to the power minus IH's. Therefore, the identity of the correlation functions of psi's, psi tildes, e to the power h, e to the power minus I, demonstrated the equality. Okay. So these are just completely identical theories. They're just completely identical theories. Okay. Now, the advantage of the bosonized way of writing the theory is that several operators it's easy to write down many sets of operators in bosonic language that are only abstractly understood in fermionic language. Okay? And in order to understand that, you say that if you take arbitrary products of psi and psi tilde, you take arbitrary products of these guys, you only get operators of the form e to the power I n h, type polynomials of h. Right? So the Charman and the shift symmetry of h will always be an integer. However, it's easier, of course, in a bosonic theory to write down the operator e to the power I k h arbitrarily. Not necessarily an integer. This is a well-defined operator whose correlation functions you can calculate. But it's not something you can build out of taking products of psi and psi tilde. Okay? So these funny operators from psi tilde language have a chance to be expressed as simple operators in terms of e to the power h. And that's what we found to be true of the Riemann sector. We found in particular the vacuum of the Riemann sector was e to the power I by 2h plus minus. Plus minus, then you remember the Riemann sector was in this spinor representation. So depending on the big state of the spinor representation. Okay? The vacuum of the Riemann sector was due to this operator. And this operator, just to remember, has dimension 1 by 8. Half k squared is 1. Okay, and all other operators in the Riemann sector were as usual. You act on the vacuum with some particular oscillator. It's like by acting with psi minus n on the vacuum is obtained. The operator due to that is obtained by multiplying this operator with del n on psi by n factorial. Okay, so that was our every set of the Riemann sector will have the corresponding terms. Okay, easy to calculate with the language. We always had it. I emphasize in bosonization is not in principle necessary, but it can make your life nice. Okay, so this was an equivalent description of this fermionic theory, which we now understand well. well enough to be able to. Why are we after vertex operators? Of course, we are after vertex operators because these are the insertions for scattering activities. We want to compute correlation functions of these vertex operators. It's nice to have them in a way that we don't. So that's the idea. Okay, good. So that was the story of the state operator map with the fermions. I'll remind you of our discussion of the state operator map. Well, I'll ask you to remind me of our discussion of the state operator map in the BC system. Let's remember the BC system that P Z with C of 0 is equal to C of Z with B of 0 with 1 times Z. That's the idea. And let's stick to the value relevant to string theory lambda equals 2. So B is expanded as sum over M 1 by Vm Z to pi m plus 2. C of Z is equal to sum over M Cm Z to pi m minus 1. Now I want somebody to help me. Somebody volunteer to determine the state corresponding to the identity. So I want to write an equation saying, so first, okay, let me start. I'll start by saying that Vm is equal to Z pi m plus 1, B of Z, I'm missing 2 pi's like crazy. 2 pi are even crazy, okay? And Cm is equal to Z to the power M minus 1, M minus 2. Okay. Now, these two expressions with analogously of B and C tell me that Bm on identity is equal to 0 for some range of n, and Cm on identity is equal to 0 for some range of n. Please fill in these ranges. M greater than equal to what? M greater than equal to what? Come on. Where is this thing analytic? Exactly. 1. Where is that thing analytic? 2. Then 2. Excellent. Okay. Great. So this was that. This was the identity of it. Now the vacuum has Vm from 0 is equal to 0 for m greater than equal to 0. Our convention was that in the 0 was sector, Vn. Whereas Cm is equal to 0, and vacuum is equal to 0 for m greater than equal to 1. Okay. Now, compare these two statements and tell me what state is due to. 1 value of n is behaving differently. One and minus 1 generate the same Hilbert space. It's just an absolute number. So what value can behave differently between these statements? Is 2 behaving differently? No, right? Because Cm continues to analyze for 2, continues to analyze for 2, and similarly B for minus 2. It's the same in one sense. Which is behaving differently? N equals 0 is not.
We have to find a state which is like that.
Which is like that. So it's some oscillator. I'm asking what n that oscillator is.
So that would be so we have to shift it by 1 on the C side. So it will be C.
So what is it? What's the state?
So it will be C.
But which? Either of the names are different.
Yeah. So.
what? Okay, I will make it different questions. I'm saying I is equal to C minus 1. You see, because C1 does not annihilate the state. So there's a creation, there's one unit of C minus 1 acting on vacuum. On the other hand, B, what is it? This state here. B, B minus 1 does annihilate the state. So what am I saying? Have I got it wrong? Sorry. It's B. Right? Sorry, B minus 1. That's it. B minus 1 does annihilate the state. Because this is annihilated by n greater than or equal to minus 1. But B minus 1 is a fermionic operator. So this state will satisfy this one. On the other hand, C minus 1 does not annihilate the state. Remember, B and C are non-zero, non-trivial commutation. Okay? So this will happen. So when this thing was fermionic, this was very simple. Okay. This was the state corresponding vacuum. The state corresponding vacuum was this state. Identity operator was this state. The vacuum was which operator? Right, the C. The vacuum was the operator C, as you can see in many ways. The simplest of which is to say that, well, the vacuum has lower energy than the identity operator. It must correspond to an operator with lower dimension than the vacuum. But the vacuum has that identity, right? But the identity has dimension 0. So it must correspond to an operator with negative dimension, the only such operator with x. Okay. And so, okay, that was the game of the PC system. Great. So now I think I've reminded you of everything. I reminded you of everything that we need to start discussing what I want to discuss. Now, okay, there's one more reminder of something that so now I want to discuss the state operator map with the beta gamma system. And this is a surprisingly intricate discussion. It's more intricate than any other discussion. Okay, so we want to discuss the beta gamma system. Okay, the only thing we need about this is we'll remember that beta of z is equal to sum over beta of m divided by z to the power m plus 3 by 2. And gamma of z is equal to gamma of n over z by m. And we remember that gamma of z, beta of 0 is equal to 1 by z, but beta of z, gamma of 0 is equal to minus 1. Okay. So these are the things we're going to use to try to discuss the state operator map of the beta gamma. Now the beta gamma system was related to the fermionic things. And fermionic things, as we've discussed several times, can be either integrally or half integrally moded. So we will have to have a different discussion for integrally moded and half integrally moded. But using our experience with the fermions, the simpler case was the NS sector. That was the case of half integral moding, because it gave you integer moding on the plane. So let's first start with the NS sector. So the NS sector, these M's belong to Z plus half. Okay? So clearly the identity is in the NS sector, it's the same arguments you want to give fermion fields. So the first question we're going to ask is, what is the operator dual to the, what state is the identity operator? Okay, so the identity operator, so let's work out a parallel to our discussion. Okay, so we have beta m is equal to z to the power m plus half beta z. Gamma m is equal to z to the power m minus half gamma. Okay, so we therefore find that beta of m acting on the identity operator is equal to 0 for some range of n, and gamma of m acting on the identity operator is equal to 0 for some other range of n. Then the ranges. This one is n greater than minus greater than equal to minus half. Well, it's greater than yes. Okay, yes. Okay. And m greater than equal to plus excellent. Okay, now what about what state does let's say that we define a vacuum state of the system. We define a vacuum state of the system. We define a vacuum state of the system by definition, by the requirement that in parallel with everything else, that beta of m on the vacuum is equal to 0 for all m greater than or equal to half and gamma of m 0 for all m greater than. Okay, have I messed up? Is our greater than equal to 3 by 2. Makes more sense. Whatever here.
That was gamma's conformal weight is half, and when you are reversing it, there is minus half. So when you are reversing it, there will be a 1 by z factor there.
Yeah.
So when gamma m is written as the integral, so it will be 3 by 2, z to the power m minus 3 by 2. Gamma m written as the integral.
Yeah. Yes, I should wait. I want a whole factor f, right? So I should multiply by z to the power n and multiply by z to the power minus half. What's wrong? Sorry.
You want to 1 by z left, right?
Yeah, if you multiply z to the power m minus half and divide by z, which is z to the power m minus 3.
You're right. Thank you. So yes. Thank you. Yes. So I should multiply this by, as you say, I should have an overall 1 by z left. This is a square root in the numerator. So I need a set of 3 factor. Yes, exactly. So this is minus 3 by 2. Thank you. This is minus. This is greater than 3 by 2. Excellent. So this is a situation that looks very parallel with the BC system, right? The oscillator that's different, that's behaving different from in the identity sector, in the state corresponding to the identity, as compared to the state corresponding to the vacuum, is which one? N equals to half. N equals half. Right? This one does something funny at minus half, which you didn't do in the state confinement vacuum. And this one does something funny at half, which you didn't do in the state confinement. So the half oscillator is behaving funny. It's being annihilated by a creation operator. By the creation operator rather than the annihilation. Okay? Now in the case of fermionic oscillators, there was a very easy way to solve that constraint. Just multiply by a factor of the creation operator. And that gives you a state that's annihilated by the creation operator, but not annihilated by the annihilation. But for bosonic operators, it's much more difficult, indeed impossible in Fock spaces. And this is the problem that's related to the following question. Suppose you have a harmonic oscillator. It's a little more complicated because there's both beta and gamma. Suppose we make it a simple angular opposition. Suppose you have a harmonic oscillator, simple ordinary harmonic oscillator, and you try to find the operator, the state in the Hilbert space that is annihilated. We all know that A annihilates matter. Suppose we try to find the first state in the Hilbert space that is annihilated by A. Does anyone know what it would be? Well, okay, schematically let's try to look at the Schrodinger explanation. This A is a mix of x plus I times b. Okay? And this is the opposite linear combination of x and I. Okay, so it's got x plus, well, plus del x, some halves and so on side, this equation is equal to 0. And with the appropriate, I mean, if it was really this equation, yeah, the solution to this is simple, right? So that's because we want to solve the equation x minus delta x on side 0. Solution to that is simple, it's e to the square root of 2. So this state is not in our Hilbert space. It's in the low-top infinity. It's sort of good that it's not in the Hilbert space because a state which is annihilated by A dagger instead of A formally has energy equals minus, has lower energy than the vacuum. Right? Because the Hamiltonian is A dagger minus half A dagger minus half, which is equal to, now A with A dagger is a plus, A dagger with A is a minus, okay, which is equal to A dagger, sorry, thank you, plus half, which is equal to A dagger minus half. So the state annihilated by A dagger will give you energy minus half. Now there's plenty of experimental evidence to show that there's no state of energy below that of the vacuum. And of course there's a theoretical reason for discarding the state, which is not normalized. It's not in the Fock space built over this vacuum. Okay, so that's the kind of situation we have here. It's an innocuous looking twist to the BC system, but it's a big difference. It's easy to find states in fermionic systems that are annihilated by annihilation. By creation. It's not easy to find states that don't exist in the Fock space. The bosonic system. Okay? So what are we going to do? Well, let's first do all our formal mumbo jumbo, then we come back and try to understand this physically. Okay. So first thing our first conclusion is that even in the NS sector, for the case of the beta gamma system we're stuck. We don't know. We don't know what the state is dual to the identity operator if we start with vacuum. Or more seriously, what is really interesting, we don't know how to build the operator that will be dual to the vacuum. If we could just sort of understand what state the identity operator was that built over the vacuum, we would be able to figure out the operator, but we don't know how to do it. So even in the NS sector here we're stuck. So first we didn't just give up thinking of it physically, we're just going to try to understand things mathematically by an effective Bosolization. Then we'll come back and try to address the question of what's going on. Okay. Oh, I should say. Okay. Well, I mean, all that we require is this. Okay, so let's see. Suppose now we wanted the operator dual to the state. Vacuum. Okay, what OPEs with beta and gamma should that operator have? Let's figure that out. Okay. So let's see. Suppose we inserted in an operator here, O. And then we wanted this to vanish. We wanted this to vanish for m greater than or equal to half. Not m greater than or equal to minus half. Okay? That would work if beta with O was order 1. Similarly, if we inserted this operator here, and we wanted to vanish for m greater than or equal to half instead of 3 by 2. This will work if gamma with O was O of z. Okay, so we are after some representation of the theory, some representation of the conformity theory, which we can find an operator that has these operator product relations with beta. Okay, so let's try to find it. Okay. Now the first thing we need to do is the following. We're going to find a representation in several steps. I'm following completely Kuczynski here. This is a very beautiful way of motivating this representation. Great, it's the Friedan, Schenker, somebody else. It's the traditional way, but it's very beautifully said. Okay. This is how we go about it. Look, in the beta gamma system, let's look at the operator beta times gamma. This operator has weight. This operator has weight 1 because we've got 3 halves and minus half. Okay, it's not really a primary operator, but just under L0 it has got 1. Okay, and let's look at the OPE of beta gamma z with beta gamma z. That's very simple. The singularity structure is very simple. Okay, what we get, the leading singularity here has gamma contracting with beta, that gives us a 1 by z, and beta contracting with gamma gives us a minus 1 by z. Okay, so the leading singularity is equal to 1 by z squared plus I. Okay? Or with a minus. With minus. Minus 1 by z squared. Two different orders. Gamma with beta was z 1 by z, but beta with gamma was minus 1. Okay. Now, let's look at the theory of a free boson. Theory of a free boson with OPE phi of z. Phi of 0 equals minus 1 log z. we're proceeding in analogy with Bosonization of the fermionic system, which by the way is the same as Bosonization of the BC system. Because the BC system is the same action as a system of two complex fermions. You remember, actually I should have reminded you of that, but you remember one of the classes we talked about how to Bosonize the BC system. It was the same way as. Right, so we're proceeding in analogy with this. And the next, you remember in the BC system that this operator, B times C, the fermion number operator, mapped to I del phi, or I del H, mapped to the shift symmetry generator, the bosonic generator. Okay? So, let's see if we can find something analogous, right? Suppose I get del phi times del H. What do I get? Well, if I didn't have the two dels, I would get minus log z. The first del gives me 1 by z, minus 1 by z. And the second thing would have given me plus 1 by z squared, but it's del with respect to the other guy. So it continues giving me minus. So I get is equal to minus 1 by z. What are we trying to do here? We're trying to find an alternate, we're trying to Bosonize this. We're trying to find another way of writing the beta gamma system in terms of some other things. Well, actually beta gamma to start with are Bosonic. So the thing we did before, it's not clear that it's going to work. I'm trying to, it's not going to work. I'm trying to motivate the actual construction that will work. I could just write it. I mean, there's construction in the end that works, but I'm trying to motivate it. Okay, now, this suggests that this beta gamma system, when written, that there's another way of writing this beta gamma system that involves a free-scale field, such that this operator beta gamma is going to map to the operator beta gamma is going to map to at least have a part that maps to del phi. Okay, so let's motivate it by this. Let's try the guess. Beta will be equal to e to the power of phi. Gamma is equal to e to the power minus phi. I may have to change these signs. Okay, so let us suggest that there is a free boson in the alternate representation of this theory, and I'm going to try to make a guess for what beta and gamma might be in terms of this free boson. It's not going to work, but it'll be useful. So let's check. The principle I use for making this guess is that it should have the right OPs with the counter. So let's check. Beta gamma at z with beta 0 is equal to beta divided by z plus something, you know? Beta gamma at z with gamma 0 equal to minus of gamma divided by z plus something. Okay. So let's compare that with this suggestion. So del phi times e to the power phi. Okay. Now this is equal to e to the power minus 1.
How is difference now at del phi?
That is us proposed. Because what we said was that beta gamma has the same singular part of OP as del phi.
Oh, fine, but now we are saying beta is e to the power phi and gamma is e to the power minus phi.
Yes, okay. Yeah, so actually that would work. That would work. It would work because, give me one minute, let me just finish this. It would work for the same way it works for the BC system. it's the just hang on. Okay, so yeah. So we let's say del phi times e to the power minus phi would be equal to e to the phi is equal to second. There are two minus signs, right? There's minus sign from the there's the minus at the lower stage. Okay, so I got this thing wrong. So I should have beta is equal to minus phi, gamma is equal to phi, and that's good. Okay, good. So you might suggest that this thing would work. Okay. Yeah. Jyotirmoy's question is how is beta times gamma del phi? Well, the way that would work would go as follows. Right. So beta e to the power minus phi times x times e to the power phi at 0. Okay. Now this thing is equal to e to the power minus phi of z phi of 0 by 2 times normal order e to the power minus phi of z plus 5. Right, so this is a product of normal order operators and they're expressed in terms of something times normal. Okay? Oh, the sign is not good. Actually. Actually, maybe it's important. Maybe you're right. Of course, the whole construction doesn't work. They didn't think it had failed with this instance. But maybe you're right. In the BC system, we had i's. So that flipped the sign. And that made it work. You see, then this was 1 over z. And then we have to data expand this way. So that's z times z phi. Yeah, but you're right. Okay, good point. So already from this thing, we see that this construction doesn't work. Okay, it just is not working. Beta gamma is not. It's a good point. It's just internally inconsistent. Okay, so you might try to make this guess, but for Jyotirmoy's reason, you would see that it was wrong. They're probably equivalently. There's another way to see that it would be wrong, which would be as follows. Actually, it is equal. Sorry, yes, I should. Yes. Suppose we looked at e to the power minus phi times e to the power minus phi. So beta times beta. What would have been beta times beta? Okay, for z. So what? So this is it. What singularity structure is e to the power phi plus this 2-point function, which is minus 1z. So 1 by z. So it's 1 by z. Okay, so let's just call it order. Similarly, e to the power phi of z, e to the phi of z will be order 1 by z. Right? Whereas e to the phi of z and e to the power minus phi of z will be order z. Yeah, okay, fine. So this is a restating of your problem. What? Yeah, what should we have had? Yes. So beta with the beta, both of these should have been. So let me write in some other color chalk what they should have been. Beta with beta should be order 1. There's no singularity, but it's not fermionic, so it doesn't vanish. Okay? Gamma with gamma should also have been 1. And beta with gamma should have been order complex. So none of them. Right. This is the restatement of the data. Okay, so none of them work. So what's going on? Well, of course, one possibility is that you doubt it luck. But there's a way to fix this up. And the way to fix this up is certainly interesting. The right answer is beta is equal to where zeta and eta belong to a conformal field theory that's decoupled from the phi conformal. So now let me tell you what the answer is. The answer is going to be, you have in order to get the equivalence of this bosonic theory, you have a product of two different conformal field theories. One of them is a conformal field theory of free boson. Okay? But the second one is the conformal field theory of two different oscillators, which I'm going to call zeta and eta, whose properties we now will discuss.
Here goes on.
No, they're found. Okay? See. So, but let's try to deduce that. What we want is for this thing to obey this. Without the del zetas, this obeys this. So, if we have del zeta of z, del zeta of 0 equals order z. We have eta of z, eta of 0 equals order z. And if we have del zeta times eta equals order 1 by z squared. This will work. Right, then the singularity structure will work. And basically, once the singularity structure works, singularities and zeros work, the same argument that we used before for bosonization. You've got the right singularities and zeros, you're more or less guaranteed to get right. With two theories are guaranteed to get identical. Okay, now how do we fulfill eta z and eta 0 being order z? That would work if eta was an anti-commuting field. Any anti-commuting field. Similarly, if zeta was an anti-commuting field, the del zeta of z, del zeta of 0 would be order z. Yeah, anti-commuting. Because at the same point it's 0.
Is it possible to figure this out with the central charges?
Yeah, we're going to check this with the central charges. You would figure this out if you assumed some structure of the thing. If you knew that this is going to hang on for a minute. Yeah. Okay. On the other hand, if we want del zeta times zeta to be order 1 by z squared. That tells us that zeta times zeta is order 1 by z. Okay. So what famous fermionic system do we know that has these properties? Come on. It's the Macy system. That's the reason I put the del behind zeta. Zeta times zeta is 1 by z, so del zeta times eta is 1 by z squared. That's why I made this del z. I mean, for this argument, this could well have been zeta, but I want this to be familiar. I want this to be a familiar relationship for zeta. Okay, so that's really great. So what have we understood? We've understood that we will get the right OPs between beta and gamma if we make the following bosonization, where eta and zeta are two fields of a BC system. Is this clear? Okay? So far we've only been looking at OPEs of basic fields with themselves. Okay? So we haven't we made no statement about what the conformal structure is, what the stress tensor is. But now we're going to change that by looking at the actual stress tensor. Okay, so the BCD system could appear with any lambda, and the free boson could have any, what is it called? What is it called? Linear dilaton, something. Doesn't make sense. V, exactly. Okay, and these could and generally will appear here. Okay, so what we've understood is that all correlation functions of this theory will be all correlation functions of this theory. So these are identical. Conformal field theories, but now we have to understand what sense they are identical, meaning what the stress tensor is in terms of these differences. Please.
What is this? I mean, the phi is not compact.
No, just an analytic boson. It's likely to be for the bosonization of the functions. Just an analytic boson. The formal level, you know how to calculate it. Okay. So now let's keep going. So the next thing we have to do is to determine question. Say. Question.
Beta was bosonic, right?
No. Beta was bosonic. Gamma was bosonic. So then you ask how did it be? The point is that the overlay of e to the power minus 5 with e to the power 5 gives us an odd power set. So the exchange symmetry has that extra minus sign. You could have asked this question about the ordinary bosonization. We took two fermions and wrote them in terms of bosonic fields. How could that have been? And we sort of discussed this. This is the point, basically. That there's the minus sign. And in operator language, there's a bigger gap. There's a construction that explains it. Okay, good. Other question. Good.
You could have also written down this in terms of bosonic fields only, right? I mean, we're considering bosonization of this.
Yes, and that will sometimes prove useful. So, during my comment is that we can further bosonize zeta system. That we can do.
But is there any specific advantage of it?
Yeah, I mean, if and when we need to, we do it. Right? But now we're familiar with how to bosonize the system, so that will be nothing very new. But it will sometimes be useful. It's a good thing. It's correct and will sometimes be useful. Okay, good. So now the last thing we want to understand is what the stress tensor of the original beta gamma system is in terms of this thing. So let's see. Let's compute T times beta gamma. You see, now by the way, this beta gamma does have its order 1 by z. So that beta gamma does have a piece that is del phi. Okay? So we've fixed it up so that there is a piece in beta gamma that is del phi. Okay? So if you look at the operator beta gamma, the part that and you bring beta towards gamma, so that's what beta gamma means. The part of that operator that lies in the phi CFT is just del. Okay? So as far as the phi CFT is concerned, beta gamma is the same as del. Okay? But now we determine what this T beta gamma is. We determine the maximal singularity. So in order to do that, we should remember what T was. We had that written down earlier in this class, but I'll write it again. So T is equal to del B, no, that is beta gamma, del beta gamma minus half 2 lambda minus 1 del of beta. Okay, now let's contract that with beta gamma. Okay, so let's say. So this contracted with this, gamma with beta gives us 1 by z, and gamma, this contracted with beta gamma. So gamma with beta gives us 1 by z, del beta with gamma gives us plus 1 by z. So 1 by z cube, so everything will be 1 by z cube for maximum singularity. We have 1, and then we have minus half 2 lambda minus 1, and then there's just the derivative with respect to z of minus 1 by z squared. So we've already seen that beta gamma with beta gamma is minus 1 by z. Derivative with respect to z of minus 1 by z squared is 2 by z cube plus sign. So that gets rid of this half. Just finish that. Cube into 2 lambda. Oh, sorry, minus 2 lambda. Yes. Yes.
The degree of freedom count, how does it go for if we introduce action statements?
The degree of the
The two field is the same, right? So, won't there be?
The true count of degrees of freedom is separate. We have to understand what the stress tensors are in order to compute this. We check. There's something here confusing here because none of these things are unity. Okay? So, it's easy to be confused about that. So you should just look at things that are, totally well defined and meaningful. Central charge is the true count. Okay. Fine. Okay. But of course, if you just want to ask, how could there be a one-to-one correspondence with the operators? That is true. You can check just in the ordinary organization. Just the fact that every operator here in this theory is produced in the OP of beta and gamma, and presumably, maybe.
In theories, you can write down operators only with one part. That's a constant part. They're not.
But that's fine. You can write these terms as well. By contracting e to the power minus 5 with e to the 5. Your term is 1. I think you would be able to write down everything with enough product. I haven't checked that. Yeah, but I think it is true because, well,
It's just therefore not easily writable operators.
right.
I mean that's the
Right.
That's the reason why you write.
But that's where the reason is right. Exactly. So let's move quickly. So this was the maximum singularity. Now we want to know what the stress tensor for the del phi system was. So every del phi system has a stress tensor that is minus del phi squared by 2. And then plus you can have a del squared phi. Right? Yeah. And let's check what A is. Yes. Let's in a minute. Okay, so I'm leaving this as an exercise. Check that A works out. A is equal to write it as half of minus 2 lambda. Okay, just in order to get it. A has to be this. Okay, so just take the OP of this with del phi, compute the maximum singularity, equate with this. Okay, now let me complete the set of exercises. Okay. Now, given this, you can now ask, what is the weight of this operator? The e to the power minus 5. Since you know what its shift charge is, you can easily compute that. But we know what the weight of beta is. So you can compute what the weight of zeta is. Okay. Similarly, you can compute the weight of this and thereby compute the weight of this. Okay. I want you to complete that exercise and show that the weights of these two fields are 1 and 0. the weights of the fields zeta and eta, or eta and zeta, I can't remember which, are 1 and 0. So it's a BC system with lambda equals 1. 1 and 1 minus 1. Okay? And that tells you what the stress tensor is of this zeta systems. Okay? And last exercise is then using this, compute the central charge of the zeta eta system, compute the central charge of the phi system, add it up, and compare with the central charge of the eta system. Okay? All of these things work out. I'm not going to work them out next class. I just assume you guys checked it all. And next class we'll then. Oh, maybe I should just give the punchline. Why do we do all this? Now that we've got this representation, you remember what did we want? We wanted the state due to the vacuum to have that property that beta with the operator was order 1 by z, and gamma with operator was equal to order z. In terms of this new representation, what's the answer? The operator. But clear, right? Either e to the power 5 or e to the power minus 5. You just check signs. Right? Because beta has term that is e to the power minus 5. Yeah, so in fact e to the power 5 will work. It's the same thing like the BC system. Because we've got two decoupled field theories. And as far as the 5 elements goes, it's exactly like the BC system. So the same construction as the BC system. Okay? So that's the punchline. In this theory, it's very easy now to find the operator due to the vacuum. Okay, I'll come back to that part in more detail next class. Let's stop now and